Hey, welcome back everybody to 10600 Math for Machine Learning. So we had some lecture notes exercises that were due today. They were due about a minute ago. So in a little while, I'm going to go over the solutions to those because we had a few requests to do that. Let's see. So. Then after that, we're going to look at linear algebra, in particular vector spaces and vector spaces of functions. So I think Q&A has a short grace period for people to submit answers, so we're going to wait to discuss the answers until we've gone a little bit past that. And instead, let's just start with our lecture topics. So, all right, so vector spaces. A lot of you are probably already familiar with the vector space Rn, right? Vectors of n real numbers. What we're going to try and do today is generalize that. We're going to try and go from vectors of real numbers to a more abstract notation, a more abstract notion of what a vector is. And we're going to try and preserve all of the nice properties that we know from Rn so that we can work with these abstract vectors in the same way that we work with vectors from Rn. And that's going to wind up giving us a lot of flexibility when we do algorithm design. So what is a vector space? A vector space is a set of vectors. So you can think of Rn as an example, and we'll see some more examples later on. Each of these vectors supports at least two operations. The operations are to add together two vectors. So if we have, that would be like x plus y, where x and y are in our vector space, and scalar multiplication. So that's a times x, where x is in our vector space, and a is just a real number, right? So real vectors support these just by component-wise operations, right? You add two vectors component-wise, and you multiply by a scalar component-wise. And in fact, that's going to be a pretty common way to implement those operations, but it's not necessarily the only way. In addition, a lot of the vector spaces that we work with, including Rn, are what's called a complete inner product space. So there's two parts of that. One is an inner product space. That means that it supports an inner product. The inner product in Rn is called the dot product, right? It's so e.g. the dot x dot y, right? And that's equal to x1 y1 plus x2 y2 plus and so forth up to xn yn, right? That's the standard inner product. And the inner product satisfies a bunch of axioms that you're probably familiar with. Things like the inner product is linear in each one of its two arguments. In fact, it's bilinear. That's what it means to be linear in each of the two arguments. And the inner product of x with itself is 0 only if x is itself the 0 vector, right? There's a bunch of axioms for inner product. From the inner product, we can define a norm, right? And that's the norm is just going to be the norm of x is equal to the square root of x dot x. Let me I've forgotten to sign into Hangout, so I want to make sure to be able to get questions from people. All right, so now I can get questions from people. Sorry for the delay. Okay, so we define our norm like this, the square root of the dot product of x with itself. And then given a norm, we can define a Cauchy sequence, right? A Cauchy sequence is a sequence that converges. It's a bunch of vectors that get closer and closer together. The formal definition is that the limit of the distance between xi and xi plus 1, meaning the norm of xi minus xi plus 1, that distance has to go to 0 as I increases. right? And every Cauchy sequence converges in Rn, and that's what it means to be complete, is that every Cauchy sequence converges, right? All right, so what the notes do, they describe how to abstract these properties away from Rn. They describe how to talk about an abstract vector space where the vectors are these arbitrary objects that still satisfy these properties, that we have addition and scalar multiplication of vectors, and inner product between vectors that leads to a norm. And the norm lets us define Cauchy sequences, and these Cauchy sequences are guaranteed to converge. So a typical example that's not Rn, and that is a good one to keep in mind to make sure that you sort of don't depend on Rn specific properties of vector spaces, is a vector space of functions, right? So you can say that a function, like this one right here, you can think of the entire function as being a vector in a vector space. Why can you do that? Well, you can take two functions and add them together. You just add them component-wise, right? So the function x plus the function x squared is just the function x plus x squared. And you can scalar multiply them. Again, component-wise, 3x is 3 times the function x. And you can define inner products between pairs of functions. I won't talk about that right yet, but we'll get into that in a little bit. And it turns out that you can set it up in a way that you do indeed get nice convergence properties in this vector space. And so we'll see in a little bit why it's important to be able to think of vector spaces whose elements are functions. But just one way that I like to think about it that is sometimes helpful, if you think of a function like this, and you think of what you do when you plot it, right? You sample the function at a grid. You pick a bunch of points, right, on the x-axis, and you evaluate the value of the function at each one of these points, and you collect the evaluations into a vector, and that vector is in Rn if there are n points that you sample at. All right, so the function is, you can think of it as like the infinitely densely sampled version of that. Like it's an infinitely long vector where there's one component for every possible point that you could sample it at. And it behaves a lot like the finite vector, right? The finite vector is just sort of a limited precision version of the function. All right, so what can we do with a vector? So here are a bunch of, this is here a drawing of R2, right? It's a two-dimensional vector space. The x's and the o's are points in R2. And what I'd like to do is, given a new point, let's say this one right here, right? We're going to represent that using the variable x. We'd like to know whether that point is in the red class or the blue class. And we'll do that by checking whether some function, checking what's called a linear threshold function of the point, right? We'll take some vector w, which is what we have to figure out, right? So I'll just label that to be learned. Sorry, I'll just label that to be learned. Sorry for the delay in figuring out how to make my phone shut up. So let's see, I'll label the w to be learned, and what we want to do is test whether w.x is bigger than some number b, right? So b is just a real number, and w is itself a vector in R2. Right? So in this particular, in this figure, I've drawn a particular linear threshold function of this form, right? It corresponds to a w that looks something like this, right? So this is the point w. The reason you know that is that it's orthogonal to the boundary between the two classes. And it corresponds because it passes through the origin to a threshold b of 0, right? All right, so this particular, this idea, right, of figuring out some function such that if it's positive, we're in one class, and if it's negative in the other class, that's called a discriminant function. And this particular function is linear, so it's called a linear discriminant function. And how do we compute it? Well, there are a lot of ways to compute it. If you take 601 or 701 next semester, you will see probably more ways than you care to see for how to compute a linear discriminant function like this. But we'll just need one. We'll use one called the Fisher linear discriminant. And what the Fisher linear discriminant is the following. So I'll draw our axes again over here, right? And what we can do is we can have the mean of one class, right, which is right here, and the mean of the, the x's were on that side. We have the mean of one class, and we have the mean of the other class, right? Sorry, I'm getting a question asking me to explain the diagram on the previous slide. So I'm assuming that's this diagram here. So this here, right, this is a vector. This is a vector in 1, 2, 3, 4, 5, 6, 7, 8 coordinates. It's a vector in R8, right? And the way we got it, the elements of the vector are the y coordinates, right? So this point here, right, is at a y coordinate. Let's say that the x coordinates that we sampled at are 1, 2, 3, 4, 5, 6, 7, and 8, right? So this here is the point 1, 1.1, right? And the 1.1 goes and becomes the first coordinate of this vector. It's exactly what you would do if you were going to plot the function. You would figure out the y value of the function at each one of the x values that you're sampling. And again here, right, this, let's say this point over here, right, this is the point 6, 1.4, right? And so we've got we've got a fixed set of x values, and these x values, they don't appear in the vector at all, right? They're just the set that we've decided to sample at. And instead what you do is you sample the y value of the function at each one of those points, collect them all into the vector as I've drawn here, and that's a vector. If we sample at 8 points, the vector will be in R8, and that vector is a finite dimensional representation of the function. And you can think of the function as being like the infinite dimensional version of this 8-dimensional vector, right? If we sampled this function arbitrarily finely, we could sample it at infinitely many distinct points, and we would have a vector that's, I'm going to put it in quotes, right? It's sort of in, sort of in r to the infinity. That's not r to the infinity, right? And I'm putting it in quotes because r to the infinity isn't really a well-defined idea, but you can think of it as being an infinite dimensional vector that's like the finite dimensional vector you get from sampling. All right, so hopefully that helps with that diagram. We'll go back here now to the Fisher linear discriminant. So we have the class means here and here, right? This is the mean of the red X class. This is the mean of the blue O class. And what we can do is we can look at the line that connects these means, right? And I'm just going to, that's the line that connects the means. I'm going to extend it now, you know, farther through the picture. And I can take W to be a vector in the direction. So I've got it in the direction pointing towards the x mean, right? The x mean and the O mean. So I've just got W then pointing in this direction, right, like that. So we'll call that W. And then we take B. Well, so here what I've got is the mean of the means, right? That's the point halfway between the means. So I'll just draw that point right there, right? And we take the intercept to be W dot this point right here so that our discriminant function, right, so our discriminant function is w dot x minus b, right, and so that will be 0 right here at this point, right? And it'll increase in this direction, and it'll decrease in that direction, and so it'll remain 0 in the orthogonal direction like this, right? So what I've done here with the Fisher linear discriminant, I've taken what's called the perpendicular bisector of the line between the class means, and that's going to be my decision boundary. All right, so that's a bit of geometry that hopefully you've seen something like this before. The definition of the perpendicular bisector is basically the line that's perpendicular to the line between 2 points and goes exactly halfway between them. All right, and that's what the Fisher linear discriminant is. It just learns the perpendicular bisector between the 2 class means. And again, if we have just some examples here and some examples here, you know, we don't really know what the true population mean is of the x's, but we'll just take the mean of all of the samples and put that here, right? So this is mean of the cross samples, right? And this one here is mean of the circle samples, right? And so, right, this mean, right, this is the same thing as this, right? Those two things are the same thing. All right, so that's a linear classifier. Now what happens if we have a nonlinear problem, right? There's no way, you know, I can draw any line I want, right, and it does an equally bad job, right? Maybe the best would be to do something like that, right? But they all do a pretty bad job of differentiating the circles from the crosses here. So we'll get rid of them. What we'd really like, right, is to have a classifier that's able to say circles are inside and x's are outside, right? So what we'd like to have is something like a quadratic decision boundary. So how do we achieve that? So the way we achieve that, and again this is in detail in the notes, the way we achieve that is through a feature transform. We transform the data using a fixed nonlinearity, right? So if we define the function phi of x here to be this function, right? This takes a two-dimensional vector, right, which we're writing as x1, x2, right? And it maps it to a five-dimensional vector where we've just kept the x1 and the x2, and then we've added x1 times x2, x1 squared, and x2 squared, right? So this gives me a five-dimensional vector. And now I can try and learn a linear discriminant on that five-dimensional vector, and I might do a better job than I could possibly have done in the original 2 dimensions. So in particular, if I learn a classifier of the form w dot phi of x minus b, right? So now here w is in R5, just like phi of x is, and b is still just a scalar, right? So if I learn a function like that, what can I do? Well, for example, well, so first let's figure out what kind of function this is, right? So it's going to be a function of the form w1x1 plus w2, right, I'll write it out, right? This is equal to w1x1 plus w2x2 plus w3x1 x2 plus w4 x1 squared plus w5 x2 squared minus b, right? And so this is a very general quadratic function. It's a completely general quadratic function in 2 dimensions, right? By setting w and b appropriately, I can get any quadratic function of 2 variables. And so that means by choosing to threshold it at 0, I can get any conic section, right? The zero of a quadratic function is a conic section, which is to say a circle, an ellipse, a hyperbola, a parabola, right, or a line. So if I can learn this W here, right, I can learn a decision boundary which is any conic section, which is nice because if we go back to our nonlinear problem, an ellipse would do a pretty good job of separating these two, the circles from the crosses. So how do I do that? Well, this is, I just use the 5-dimensional vector space instead of the 2-dimensional one, and I pass it directly to the Fisher discriminant algorithm, right? So, right, just like before, I had the expected value of x, right? Now what I'm going to do is take W to be the expected value of x given that the class is the cross class. I need to do something to distinguish the cross from an X in my handwriting. I'm going to just put an underline under the class label. So that's the underlined version is the class label, and the X is the variable. Right? And instead, so we had E of X before, and now what we're going to do is E of phi of X. Right? And then the same thing, minus E of phi of X, given, and then the other class was the circle. And again, I'll put an underline under it to say that's a class label. Right? And then the same thing, right, B is equal to W dot, the mean of the two class means, right? So that's a half times E phi X given cross plus E phi X given circle. All right, and if you do that, the picture is in the notes. I didn't copy it here, but it looks exactly like this, right? You get an ellipse that does in this case, perfect job of separating the circles from the crosses. Okay, so that kind of feature transform, that's really common in machine learning. If you want to be able to learn a nonlinear function, one good way to do it is to take your points and use a fixed nonlinear transform that you don't have to learn and map them up into a higher dimensional vector space, and then learn a linear function, because it turns out to be much easier to learn a linear function that maps those to your discriminant value, right, which is positive for one class and negative for the other. All right. So here's another example of a discriminant function, right? So if we have this data here where the crosses are sort of scattered out and the blue are clustered near the horizontal axis, you might want to learn a discriminant function that looks like this. And this is a nonlinear discriminant function, right? Before we had a linear discriminant function of the form w dot x minus b. But in general, we might want to learn a nonlinear discriminant function. And in particular, this discriminant function here is not a bad one for this classification problem. And so, so far we've looked at how to learn a nonlinear discriminant function via a feature transform. And hopefully everybody's good with that. The really powerful thing then is going to be to learn the discriminant function directly, right? Rather than representing it as some finite set of coefficients that we're trying to learn, right? Where we learn, for example, the coefficient on x squared. We can think of just looking in the extremely flexible class of discriminant functions that's, let's say, all square integrable and infinitely differentiable functions on the unit interval, right? So if we could learn a discriminant function out of that class, we'd be able to solve almost any classification problem. And to do that, we're going to have to go back to this idea of function as vectors. And so this slide is just another example of functions as vectors, right? So what we've done here is we've sampled it at 31 points as it happens, and we've taken one function this way, this is a vector, and another function sampled the same way, another vector. And if you add them together, because remember you can add pairs of vectors, you get another vector here, which it looks like, you know, a sloped version of the, it looks like what you would expect from combining those two functions. So what we're going to do is we're going to create a vector space of functions. So what does that look like? We're going to take functions of the following form. We'll call a function q sub x, and that function has an argument which we'll call y, and here x and y are both real, and we'll just define that to be e to the minus 1/2 x minus y squared, and actually we'll just do that, x minus y squared, right? And so this here, this function, this is q sub 0, right? And this here, we can make a vector space by taking all of the functions, excuse me, all of the functions we can get by adding together multiples of these functions. So that's called a linear combination. And this particular plot here is q sub minus 2, right? There's one centered here, minus 1.5 q sub 0, right? So there's another function centered right there. And then I've centered a third one at, I forget where I centered the third one, whether it was, I think it's just q1, so I've centered it right here. And I multiplied it by 0.75 times q1, right? And so you can see I can get a lot of different functions by adding together multiples of these, we'll call them basis functions. And actually, in particular, if I pick any distinct set of centers and any distinct set of weights, right? So if the centers are at different points, then I can take any set of weights and multiply them and get a new function, right? So I can get infinitely many different functions this way because there are infinitely many places that I can center one of these basis functions and infinitely many coefficients that I can use to add them, to multiply, to scalar multiply them and add them together, right? And so this satisfies everything we need for a vector space, right? It's got the vectors, it's got addition between vectors, which is just component-wise addition of functions, and it has scalar multiplication, which is just, again, component-wise scalar multiplication. So that's a vector space. So if I go back here, right, I can write a different version. So the general version of this, right, I can write q sub x comma sigma of y is equal to exp of minus 1. And now let's say that x and y can be vectors. So I'll just take the distance between x and y squared, and now I'm going to divide by sigma squared. Right, so there's two generalizations here. One is that x and y are now allowed to be vectors instead of real numbers. And so for example, they could be in R2, right? And the other generalization is the sigma squared. So sigma is called the kernel width parameter, and it tells you sort of how wiggly the functions are going to be that we can get. So this is just an example of 3 different functions that I can get using sigma equals 0.1, right? So this one is, it's just a vector that's in the span of q sub x comma sigma, right? The functions q sub x comma sigma where sigma is equal to 0.1, right? And this one is also such a vector, and this one is also such a vector, right? Whereas if I choose a wider kernel width, right, I get much smoother functions. These are also vectors, but they're in the span now. This is in the span of q sub x sigma for sigma equals 0.5. And so in 2D, it looks a little bit like this, right? Here, I think I chose sigma equals 0.07. And this is just a two-dimensional function that's in the span of that set of basis functions that I described a couple of slides ago. All right. So I've just described this idea of linear combinations and of a basis. So in the lecture notes, I also described two additional concepts, which are linear independence and dimension. So if you have a set of vectors, if you can make a linear combination of those vectors be 0 without the coefficients being all 0, then those vectors are said to be dependent. And if you can't, then the vectors are said to be independent. And a basis is it's a maximally large set of independent, linearly independent vectors. And the dimension is the size of a basis. Again, all of these concepts are described in the lecture notes. The one that may be less familiar to people is the idea of an infinite dimensional vector space, where you can get an arbitrarily large set of linearly independent vectors. All right. And so now if we have all right, I am getting questions. People are apparently confused about the meaning of sigma, right? So let's go back here. This is my set of functions, right? So I'm defining q sub x sigma according to that. And so if I take just one of these, let's take it in one dimension, right? This is, this one here has sigma equals 1, right? And if we draw another axis, right, minus 3, 0, 3, we could, if we make the function much narrower, right, like that, this corresponds to a small sigma, right? It'll still be a bump function, more or less of this same shape, subject to the limit of my drawing ability. But if we make sigma small, it'll be narrow like this. And if we make sigma large, right, we'll have a much wider function, right? It won't go down to 0 until it's way out here, right? And I'm going to stop drawing because of the other set of axes, but right, this is here a large sigma, right? So if you want to, you can plot this function in your favorite plotting program and just plug in different values of sigma and different values of x, right? So x here is the center, and sigma determines the width of the bump. And so I have some examples here with different sigma. People can't open the second set of lecture notes. That sounds like a problem that I need to fix. It could be that I made a typo in the URL, so let's go and check that. Oh yeah, there is a definite problem with the URL there. I apologize for the problem. All right, I've just checked, and subject to the limits of my network connection, yes, there we go. So now people should be able to open the second set of lecture notes. Apologize for the typo in the link. So if you just go to the syllabus post, reload the syllabus post, and click on the vector spaces and dimension link again, you should be able to open it. All right, so we have now sigma. And we have this idea of making a vector space by putting together linear combinations of a whole bunch of functions from a given class. And that's going to wind up being an infinite dimensional vector space. And if we now work in this infinite dimensional vector space, again, the notes go into a lot more detail. But if we wind up working in this infinite dimensional vector space, we can learn a nonlinear Fisher discriminant, an infinite dimensional Fisher discriminant. And the recipe is exactly the same. We have the expected value of some feature function phi applied to our points in either the cross class or the circle class. And we take our we take our discriminant function to be the inner product between w and phi of x, and we learn w according to this formula, right? Now, the difference is that phi of x, instead of being, let's say, a 5-dimensional vector, phi of x is an entire function, right? So we're going to take our points, which are here in 2-dimensional space, and we're going to map the point x, right? So let's say that could be this point right here. That could be x. And we'll take q sub x of y, that's this entire function, which is e to the minus x minus y squared over 2, right? And so we're going to consider that the feature transform of our point. And it's an infinite dimensional vector, right? The feature transform of x, phi of x, is an infinite dimensional vector, but that's okay. There's nothing wrong with infinite dimensional vectors. They're still vectors in a vector space. And we can still take the mean of phi of x conditioned on our being in the cross class, and the mean conditioned on being in the circle class. And those are going to be vectors, again, in our infinite dimensional vector space. We take their difference, and that is the w in our linear discriminant function, right? So it's important. This example should hopefully illustrate why it's important to get away from the idea of a vector being just an element of R3, right? A list of real numbers. A vector is a much more general object, and in particular, it's very helpful a lot of the time to consider entire functions as vectors so that you can take learning algorithms that are designed to work on vectors and make them work on entire functions instead. All right. So in particular, it can get pretty confusing to think of all of the different types of objects that are floating around when we're doing this, right? So we have our examples, right? These are the crosses and the circles. These are points in what I'll call our example vector space E, which is going to be, in the examples so far, R2. Then we have feature vectors, and these are going to be we apply our feature transform to one of our examples, and I'll call that the feature vector space, right? It's the space of feature vectors. And in the notes, that was the vector space H that we created by taking the set of all linear combinations, the span of our Gaussian bump functions, e to the minus x squared over 2. Right? So then the feature function itself, right? So a feature vector is something like phi of xi. A feature vector, the feature function itself is a function that maps examples to feature vectors, right? So its type is a function from e to phi. Then we have discriminant functions. They take an example and give it a real number, and the real number is positive for one class and negative for the other. So they're functions from e to r. And so an example would be w dot phi of x minus b, right? That could be an example of a discriminant function. Let's see. I should have said here, instead of RKHS, I should have just said vector space. It turns out, if you happen to want to go on, that this particular type of vector space that we've constructed is called a reproducing kernel Hilbert space, or RKHS. You don't need to know that for this class. I just accidentally wrote it there. So what I meant to say was just a vector space, which is a set of functions that take examples to reals. And again, I don't need, I left that on the slide accidentally, so you don't need to know about that. But you do need to know about an inner product, which again I defined in the lecture notes. And this takes our vectors, our feature vectors, it takes a pair of them and gives a real number. Right? And so it's good when you run across a new object to think about what its type is. And it's always good as well if somebody tells you to apply a particular function to a particular object to make sure that the function is of a type that can actually apply to that object, right? So for example, if somebody told you to take the dot product between, let's say the dot product, this dot product, the inner product in H between two examples, you couldn't do that, right? Because this inner product is only defined on entire functions. You would have to apply the feature function to an example first before you'd be able to apply this inner product to it. All right. So just type checking is always a good way to, as always, keep your mind straight about what operations are allowed to be performed on which objects you're thinking about. And so I also want to point out that a function in our vector space H can be viewed in a lot of different ways, right? So we're thinking of it either directly as a vector in the vector space. We can also think of it as this third line, a function that takes an example. Actually, maybe even a simpler way to say it. Right. A function that takes an example as an argument, right? And again, you actually don't need this. This is probably the better way to interpret it. So you can take this function in a vector space and interpret it just as a function that you can apply to an example, or you can interpret it as a vector, or because we have an inner product on the vector space, you can determine it. You can think of it as a linear function, right? So if you apply it to, if you take its dot product with another vector, right? Just like you know, w dot x is a linear function if these are both for w and x in R2, right? This is a linear function of x. You can also take f and interpret it as a linear function on our vector space of functions. And so again, it's important to think, to keep straight when you're thinking about this object, there's multiple different interpretations of it, and it's always good to keep straight in your mind which one we're thinking of at any given time. All right, so I'm gonna, people should feel free to continue to ask questions about this set of lecture notes, but I'm going to go back and now talk about the exercises that were due today, since they've been due for a little while now. So maybe the prototypical one is this exercise 4, right, which is incorporating evidence. So this is the one where you had a weighted die, and you roll it, and a friend tells you that it might have that it was even, but the friend might be lying, right? So as always, whenever you start with some information about what's going to happen, you write it down as a probability distribution. And so we're given as an assumption that P of x is equal to the table 1 over 21, 2 over 21, all the way up to 6 over 21, right? So that's the information we start with. Now we roll it, and our friend observes it, and our friend, let's say that we want to know so the friend says it's even, right? So we want the probability that the friend says even given x, right, for each possible value of x. And that's, you can also write that down as a table, right? And that is, well, if the die roll were actually 1, that's odd, so your friend should say it's odd, but with probability a quarter, your friend lies and says it's even. If it's 2, he should say it's even, but with probability a quarter, he lies, so he only says it's even with probability 3/4, right? And we can just fill it out that way until we get to the end, right? And so, again, we can represent the evidence that we've gotten as a table, right? So the uncertain thing is x, what is the value of the die roll? We have some information from the prior probability, we have some information from the evidence, and then we always, whenever we have a prior probability and some evidence, we want to combine them using Bayes' rule, right? So P of x given that the friend says even is equal to P of even given x times P of x. And then it's going to be divided by some normalizing factor, right, which I'll call eta. And how do we get the normalizing factor? Well, we know that the conditional distribution of x, right, that's a distribution. And so over all possible values of x, it has to sum to 1, right? So we'll get eta from the fact that sum over all values of x, P of even given x, P of x over eta has to equal 1, right? And a common mistake was to try and sum over this argument, right? So it's not even a probability distribution in this argument, right? The thing on the right-hand side of the conditioning bar is side information that you have, and there's no reason for your probability table to sum to 1 over your side information. It only sums to 1 over things that are an actual probability distribution, which is the stuff to the left of the conditioning bar, right? So what do? We multiply these, to get this numerator here, we multiply these two tables, right? We have a table for P of even given x, we have a table for P of x, right? And so when we multiply it, we get a quarter from this times 1 over 21. Then we get 3/4 times 2 over 21. Then we get 1/4 again times 3 over 21, right? All the way up to 3/4 times 6 over 21, right? And it's pretty easy to do that using a calculator or any programming language. And then you take that vector and you sum it, and that gives you eta, right? And then the answer is just, well, it's the fifth element of this vector, right? So actually, let me write out the remaining missing two elements, right? So 3/4, 4/21, 1/4, 5/21, right? So I'll put commas in between them to show they're distinct, right? And so we want to take, our answer is just 1/4 times 5/21 divided by eta, where eta we got by summing this entire vector, right? So this was a one that confused a bunch of people, and this operation of taking an uncertain quantity, in this case the die roll, writing out its distribution, multiplying by some evidence using Bayes' rule, and renormalizing, that's an extremely common operation with probabilities, and so it's a good idea to become familiar with it. All right. The other one that we got a bunch of questions about was the first pair of questions, the one about the sprinkler system. So let's get a fresh page here, right? And so again, this is a question of multiplying probability tables, right? So we know from the beginning, from an assumption, that P of GRS is equal to P of R, P of S, and times P of G given R and S, right? And so this is a, right, that is a 2 by 2 by 2 table, right, where it has one argument for R, one for G, one for R, and one for S, right? And so in particular, let's just write out these tables. P of R, we know that P of R being true is 0.1, and so P of R being false is 0.9, so that's one table. P of S being true was 0.3 and false was 0.7, so that's another table, right? And then this is the big table. So it's also 2 by 2 by 2. And it's given as an assumption, so I'll just write it out in two layers, right? 0.9, 0.8, 0.8, 0.1. Actually, let's write it, we'll write it this way. And then the second layer is 1 minus, you're given only one of the two layers, but you know the second layer is 1 minus the first one. So it's 0.1, 0.2, 0.2, and 0.9, right? And just to be clear, this half is G equals true, this half is G equals false. On the rows, right, on the rows is R, so true is up here and false is down here, and on the columns is S, and true is here and false is here, right? So the best thing to do is to just multiply out all of these tables using the rules for multiplying probability tables. So you can broadcast, or you can use the expression to get each entry individually, but you'll get a 2 by 2 by 2 table, right? So I'll draw it in two layers. Again, G equals true, G equals false, R on the rows and S on the columns. And so, for example, to get this element here, right, we just take the corresponding element here. And by the way, I've made sure that I wrote out this table and this table in the same indexing. So the elements are in the same order between these two tables. It's important to do that. Otherwise, you can transpose to make sure that it happens. So we copy the element over from this table. Here's the 0.9. And then we multiply in this table, right? So R is true in this cell, so we take the true element of that table. So times 0.1. And then S is, because we're in the left column here, S is true. So we have times 0.3, right? And I'll just pick an arbitrary other element here to fill in, right? So we'll copy over the 0.2 times, and now r is false in this one because it's the lower row. So we get 0.9, the false element of r. And we get s is true because it's the left column of this layer, so we get 0.3. Right? And once you have that table, right, you fill out all 8 elements of that table, you've got a joint probability distribution of G, R, and S. And then you can just answer question 2 directly by looking it up in the table. And you can answer question 1 by marginalizing the table, right? You have to. This is now a joint distribution over 3 variables, and you want to marginalize. Sorry, this is for question 2. You can't just look it up. This is a joint table, so you have to make the conditional table by taking the part of the table that's consistent with what's given, G equals true, S equals false, and renormalize it to be a probability distribution, right? So G equals true, S equals false is here, right? Those 2 elements. So you renormalize them to be a probability distribution, and then you can read off the answer that you want. And then for 1, you have to marginalize first, right? So there's no S in the expression, just an R and a G in the expression you're asked for. And so you marginalize out the S, and then you condition on G equals true. And then you have the answer that you want. All right. So if people had more questions about the problems that were due today or about any other problems, please make sure to text the TAs, and I can go over them in the remainder of lecture today. I'm looking through, again, the lecture notes for today. We've covered the definition of vector spaces. We've covered properties like being a basis, linear independence, the idea of a linear combination, and we've gone through in quite some detail the example of using what's called the Fisher discriminant to learn a classifier, either a linear or a nonlinear classifier in these vector spaces. And so you should make sure that you are comfortable with all of these concepts, in particular with infinite dimensional vector spaces. And I think if people don't have any more questions, we'll go ahead and end the lecture for today a few minutes early, 20 minutes early. And next time around, we're going to talk about, we're going to continue talking about linear algebra, and in particular, we're going to talk about linear operators on vector spaces. And I should say, by the way, we decided not to have any in-class problems today, although we may announce some lecture notes problems later this evening to be due at the beginning of Wednesday's class. The other thing I should say that's a bit of administrative detail. I have office hours today, starting now. I have no office hours on Wednesday because I'll be traveling. So if you have questions for me, make sure to ask them to me in office hours today, or you can post them on Piazza or ask one of the TAs either on Piazza or in their office hours. All right, and so if there aren't any more questions, I think we can go ahead and end the lecture now. Thanks.